have three super speakers lined up this afternoon. And our first one, probably on my right here, is Dr. Martin Eisenberg. And Martin is the founder of Rapid Lasso Germany. And Martin specializes in geometry processing large LiDAR point clouds. And I think everybody knows the flagship product of Lasso, which is LAS Tools, the LiDAR processing software. The important about Martin is also known as a vocal advocate of open LiDAR formats and has been involved in shaping the LAS exchange standard. And also, he's an active promoter of the free open source LASzip compressor, and that's what you're well known for, definitely. The title of Martin's paper today is LASindex, Simple Spatial Indexing of LiDAR Data. And it's a pleasure to introduce you, if you don't know him already, to Martin Eisenberg. Martin, over to you.
Thank you, Alistair. Hello, everybody. So my title was Simple Indexing. So it's still simple. It didn't fit with that font to make it nice on the first slide. So my name is Martin Eisenberg, and I have a company that I just founded. It's called actually Rapid Lasso. Lasso alone wasn't quite fast enough to, get the message across. So before I start on spatial indexing, I want to give you a quick update on LASzip that I introduced last year here. So, you all know that LiDAR has literally exploded into our faces, and fortunately we got away from the bulky ASCII formats very early on due to the foresight of the ASPRS, and they create the LAS format. But still, also it was efficient to parse and seek. You have very many points creating terabytes of data. So, because I really liked compressing things, I one day decided to also compress LiDAR points. The alternatives at the time was standard compressors, generic compressors, which work, especially WinRAR works fairly well, but it's very slow and you can't deal with the data in the compressed format. Then there was a solution almost at the same time by LASindex, which had a price tag that scared some people off. And then there was LASzip, which came at a different price tag that was more inviting. So what is LASzip? Well, LASzip is a LAZ file instead of LAS. It's lossless, fast, high compression, tested across a lot of data, and most important, it's free. It's also supported by major software companies now, and that's a bit different from last year when it was sort of just in the trenches still. If you want more details, go on YouTube and search for LASzip, and you see me talk a bit more about the details. Here you see some software companies that have already embedded native support for LAZ format into them. For example, when you export your LAS data, your point clouds with the RiProcess, you can directly export into the compressed format. And there is lots of LAS already on the internet. The Minnesota DNR put almost the entire country online. Tons of counties, you can FTP them. The National Land Survey of Finland decided to only use LAZ in their open data campaign that started, I think, in May this year. So you only get it as LAZ. Open Topography, NOAA provides LAS as a download option outside of the firewall for much faster batch download. And let me give you a LASzip user tweet. I love quoting things from Twitter. It's really hip. That's what Kirk Waters said, who actually did the compression of all the NOAA LAS holdings. And finally, it did win an Innovation Award in the meantime. Okay, but now on to today's topic. That was just a little update on what has happened to last year's. Spatial indexing. What is spatial indexing? You only need it when you want to have efficient access to a subset of the points in a large file, or in many large files, or in many small files, or whatever. So the idea is you want only the points that fall into the red rectangle, for example. Or maybe you only want these points here. The other reason to do spatial indexing is if you have a tiling of that data set, and you want to do processing in a way so you don't have boundary effects along the edges of the tile, then you basically need to get from the other tiles sort of a buffer around to enhance your current tile, so you would get rid of the boundary effects. And yet another thing is to probe your data set at various locations, maybe for control checks. You know, you have quality, you have checkpoints, and you want to see if the height matches up the one you collected in the LiDAR for quality control. And if that file is 1 gigabyte and you have to load it all to get to these locations, then you have a very slow process. And you don't know where to look in these files, because these files are kind of, the order in these files, you know, here's some typical order, is kind of, it can be anything. There is no definition of in which order files the points have to be in an LAS file. They can be, you know, in this order, which is probably the result of some kind of processing and some kind of tile structure that may have been retiled several times. A little bit of the flight structure you see still there. Let's see what we have here. This is just a small piece of a single flight strip. Or what do we have here? Here you see several strips of a flight merged together into a tile that seem to have in a different projection. That's why it's a little rotated in that projection now. That's actually Toronto downtown. It's a classic LiDAR test file from Optech. But you don't always need spatial indexing. So if you don't do any of the things I just said, you know, these probing, and you don't need it. If you just compress everything, reproject everything, filter everything, any kind of batch processing that does everything on a point-by-point basis, like if you run any of these lastTools commands, you know, for those who are familiar lastTools user, there's no need to create a spatial indexing, because there's no benefit of you wouldn't exploit it. So, what are the choices you have when you want to do spatial indexing? Well, the most obvious one is to use a spatial database. And there are several choices available. What you have to do, you have to take your LiDAR data and insert it into the database. The database then has some very clever strategies to reorganize your points internally. So when you ask it for a particular set of points, it's very efficient in giving you only those points without reading much else from the disk. And that gives you efficient read and write access, if it's in most databases. Now, what's the disadvantage? Well, the disadvantage is that first big step. You have to put all your data, 5 terabytes, into the database. So you create a second copy. Well, not only creates it a second copy, but it may take a few days until it's loaded into the database. So before you get to do your first query, you know, you may have to take a little vacation. So I'm not saying this is bad. This is one of your choices. Now I'm presenting you another choice today, and that is super lightweight kind of database. And you just leave your LiDAR files in the original place. Whatever it be LAS, LAZ, shapefile, bin file, it works on all binary formats. And you create for every file a tiny LAX file that has the same file name, but an ending called .lax. And it's very small. It's usually less than less than a promille of this size. And whenever it's present, and you use lastTools, all queries that are area of interest queries will be accelerated without you having to do anything else. If you use laslib, the library, same thing. If the lax file is not there, it will behave the same way. You just have to wait much longer for the data to arrive. And what's the drawback? Well, because I don't reorganize the data, I leave the data just as it is. You can't have random data. If your data is sort of random, then it's not possible, but that's really never the case in LiDAR data. I've never seen a truly random data set. And it's only read-only, like I can't write it back. Well, at least for now. So before I talk a lot longer, let me just give you an intuitive demo. Can you read that? Maybe. So I'm in the scary command line here, and I'm listing the contents of a directory called Spatial, where we have two files in here. An LAZ file that is uncompressed, it would be 3.7 gigabytes, but it's only 420 megabytes compressed. And a small LAX file, it's really only 0.1% of the size of the LAZ file. And if I now view that file with the last viewer, oops, that's not right. Oh, let's make it a bit bigger. So last view is a very, very simple viewer that instantly starts rendering as soon as it starts. So it's decompressing the big file right now, and it would continue to do so for the entire 3.7 gigabytes of loss, but I will press pause right now to get more interactivity back. And now I press capital Q, and then it shows you the contents of the LAX file. So the presence of the LAX file means you can press Shift Q in the last view and see that blue adaptive quad tree here. So what does this quad tree mean? This quad tree is used when you do queries. I can now press little q on one of those cells, and now I see in blue the points that will get loaded when your area of interest query overlaps the blue cell that I am picking here. And you see, I'm certainly reading a lot more than I have to. And that's okay, because I'm only looking at a single cell here. And usually when you query data, you will query not just a single cell, you will query sort of 500 by 500 meter or 100 by 100 meters, and not just these tiny cells. So there will be some overhead. But the alternative is to read the whole file. So instead of the whole file, to read the contents of this cell, I only have to read the blue points. Another nice thing that the presence of these LAX file gives you, in my really not particularly beautiful GUI, you see a little preview of where the data actually is. So in this data we have two flight strips in that bounding box that are diagonal. And oops. Now I can go and pick, and so picking is basically exactly what I meant with an area of interest query. We pick in that little bounding box here in the corner, and now I say, let's view that. Now this one is at the very, very end of the 3.7 gigabyte uncompressed or 400 megabyte compressed file, and I instantly get it, rather than having to read through the whole file to find where are these points. And that is basically what simple spatial indexing with LAX is. Okay, let me give you a little bit more detail. So every cell is a set of index intervals. So all the cells you just saw, they have an index, a quad tree index. They have a number of points that they really are inside the cell, and a number of intervals. In this case, I just made up some numbers, 8 intervals, for example. And these intervals basically point into the massive LAS file and say where are the points that I need to load for this particular cell. And you will then use one of the commands that are offered by LAStools or LASlib, in any of these inside commands, to say give me only the points inside the rectangle, inside the tile, or inside the circle. Which means you will only, for example, ask for give me only these points, and what will happen then, all the intersected cells will get merged. So you take the first one, get all its intervals. Now you go, get the next one, gets all its intervals, but you don't read anything yet. That you do before, that's doing the query. You do that for the third one, get all its intervals. And you do that for all the cells that get intersected here. I didn't do the animation for all of the cells because it's very time consuming making those. I hope you appreciate that. And then you basically have a merge of all these intervals, and these are the areas you need to read. And then the red areas you need to clip against the red rectangle. That's pretty much all it is. Sounds very simple. Let me give you a few more details. about the implementation. So I chose a quad tree, and somebody will now say, why did you choose a KD tree or some other tree? It's because me and the quad tree, we go way back. That's why. No, I've been working with quad trees a long time, and I just like them. And for me, they did the job as far as I can tell. So quad tree is very simple. You saw the first level. Here you see the second level. We recursively subdivided, and I chose an order that is a Z ordering. And you see here how the indices, how every cell has a unique index. And the index of the cell not only specifies the cell, it also specifies its level, like how deep it is in the quad tree. So just by saying a very high number, you know it's a very little cell. And but I only show the first 3 levels here. And what you saw earlier, this thing, is nothing else but one of those, but now it's not fully subdivided everywhere. It's adaptively subdivided only in the places where you have data. So what this LAX file really is, it's just nothing else but the description of a quad tree. So on the left, you see an example LAX file. That's really what's in that file. It's information about the bounding box. Okay, bounding box. And now, this is a very small LAX file, just for the point. We have 9, that is the index of the cell. Just, I know 9, I can construct this partial quad tree here, because I know I have the cell number 9, and it's got to go up all the way to the root. And I construct this quad tree because I will use it later for the queries. So when I actually do a query, I use this to decide, am I intersecting cells or not? That's why I need to actually construct the quad tree when I read the LAX file. And next one. And you see the intervals are now getting associated with that cell, the index intervals. And in this case, we had 4 cells. And in the other cells that are only in light gray, there were no points. So the outline you would now see in the last view viewer would basically be the outline drawn around all the darker blue cells, and you would know already that it's not a full tile. Of course, if you now do a query, in this case, all you would have to load is the intervals from cell 4 and clip them against the triangle, the rectangle. Here you would have to load cell 9 and 11 after merging the intervals first. So you always merge those intervals. And in this case, you would have to merge the intervals of these 3 cells that get overlapped. So that's how simple it is. That's why I should have really had the word simple in front. Now this is the most difficult slide now, because the most stuff will happen on the screen. How do we create this quad tree and the intervals? Well, in the first step, we just compute the bounding box. And we usually don't have to do this because the LAS files have it in the header. But if you were to start with a file where you're not sure if the bounding box is correct, or I'm not sure if the bin files have header information, then you would need an additional pass to create that. Then you decide on a grid resolution. Here you need to know, am I airborne, which this was designed for, or am I mobile, where it also seems to work according to what people have told me. So let's say this is our lowest grid resolution, our lowest. We may coarsen it later. And then you process the points one after the other. You just read them, but you don't store them. You just read them and insert them into this grid, and you keep track of these intervals. So there comes point number 1, point number up to 4 we have now. We go on up to, we hit the next cell. You see how these intervals build up? Now we have point number 10. That's back in the first cell, but because the jump is smaller than the very small index gap size 10, we just include it in this interval. Also, we will now read more points because we include those that we jumped that are in the other cells, really. And this is because it doesn't make sense to have really small intervals, because every interval means an fseek. You seek in your file. Now, if these steps are just you seeking like 75 points, well, every point is 20 bytes. 75 times 20, you know, I can't do that math. You do it, but it's very small. It's probably below the page size. So you're going to read everything anyways, and fseek will flush your buffers. It's not good. You want to do fewer big seeks to get performance. And so on you go. As the points come in, you update your intervals, and whenever it's bigger than the last one, you basically start a new interval. I got tired, you can see, of doing that in tech. And then there's one more step, you merge cells. So when you have these cells with very few points, there's some threshold for that, of course, that you can set. Like in this case, these cells, I just say they don't have enough points to warrant being their own cell, so you can just merge them into one cell, and you merge the intervals. And one more last thing, if you want to have maximally at 20,000 intervals in your entire lax file, you can say, well, merge all the intervals that have really small gaps still remaining until I'm at only 20,000 intervals. This assures that your lax file size will never grow too large. And that's about it. The result, you write into the LAX file, the bounding box and all these intervals. That's it. But you don't have to do this because I already did it for you. So there's a tool called LASindex, which is open source and has even a little GUI. And you see I have some very simple presets, airborne and mobile, which basically will change the tile size from 100 meters and a threshold of 1,000 and a minimum point number of this and this to a tile size of, I think in mobile I use 10 meters by 10 meters as the smallest cell size. But you can experiment that by going on the custom button, and then that's right here, and try your own settings. I must say I had planned to do a lot of work and get that very well figured out. But I got so busy with Rapid Lasso that I didn't have the time to. So I can only give you a little bit of performance detail. I don't really have time for the demo because then I have to skip too much at the end. You already saw a demo. I got Christian Ginsler gave me, he saved my presentation by giving me this nice performance result. It's all of Switzerland stored in 41 billion points, stored in the intranet. He did 923 area of interest queries, each one with last clip by clipping against a shape polygon and then writing the points to a little file. And with lax it took 50 minutes, and without lax it took about 10 times longer. And I don't think his tiles are the best way to actually use LASindex, so this is just a very rough guess what you sort of can get, or more or less. Because the ordering per tile has sort of has quite an impact. Now let's look at this real quick. Here you see a nice piece of land. You press large Q, and again you see the tiling of the lax file, and you press little q, and you see which points are in every tile, in every cell. So for this cell you would load all the blue points. You know, for this cell you load all these points. So that looks pretty good. You know, it's very localized. But now let me skip to this one. So what does this number mean? This number means if I read every cell once, I will read the whole data set 1.6 times. Now here, it has a high number, and high numbers are bad. That means if I read every quadtree cell once, I read the whole data set 5.9 times. And you may already know the answer why this is if you've seen the order of the points coming in here. It's a very small tile, it's only 500 meters across, I think. And look at these, look at the many points I need to load when I click on one of these cells. That's because it's basically one flight strip, and I don't know how many points it has across, 1,000 or 400, but it's below the threshold. So all the flight strip lines that go into the next tiles will get merged into the current one. But this is really a very small data set, so if you tile a little bit bigger, it won't look so drastic. But what is the worst case? What shouldn't you do when you use LASindex? And that's sorting along an axis. Actually, you should never do that. resort your points along one axis, I really don't like it. Here you see a data set called Lincoln.last. It was sort of one of the first ones around. A lot of people use it for experiments. You've seen the point order, and if I now turn on the quad tree, it looks still pretty harmless. But now if I pick that quad tree cell and I look, oh boy, you know, you have to load, to get this little cell, I have to load everything, and everything, and everything. Now, if I want the border of that cell from this side, that means I have to load the entire tile anyways. Of course, if you want the border along the other side, it's very good, because then it falls all into one cell. But this is really not a nice order. It's been researched in many other fields, image storage and so on, that a line-by-line ordering is not a good idea for a very large data set. So fortunately, there's a last tool for that. You run last sort. It creates a Z ordering that looks like this. And if you then turn on your quad tree, then you get these very nice confined, localized number of points you need to load, and the factor goes down to 1.2, which is very good, because 1.0 would be the perfect one. Okay, that was as much as I want to say about LASindex. Now, a little preview. I'm using this plug here. You heard a lot about pulse full waveform at this conference. I've been working for about a year now on a new format to store full waveform in a native format, just like LAS, but not LAS. You know, sort of LAS is here, pulse waves is here, and they are like companions. They're not competing with each other, they're complementing. And the community got involved quite a bit. It is open format, vendor neutral. I try to reach out to all the vendors. You know, if you're in the room, you know I've tried really hard to mail to you and to get you involved, and many of you answered. The version 0.2 prototype has just been released. It's one pulse file, it's one waves file, and I'm also saying that it will be also spatially indexed. It's compatible with LAS format, and here I mapped all existing waveforms that I could get my hands on to the format and store them in the format. You see the Elvis sensor from in the top. So what you see here, it might be a bit confusing. You see the first and the last sample of every pulse. You see in red the outgoing pulse. You see in blue the returning pulse for one particular pulse. And then you see here a whole row of pulses in the terrain. I think this here is a data set from Optech. Here, that's also a data set from Optech. Here you see some Regal data. Actually, Regal already implemented it into RiProcess, into their experimental RiProcess version. And because that data set looks so nice, let me show you a quick demo, and then I'm done. So this is pulse waves. You see the last and the first sample of every wave that is kept. And then you can basically you can pick different start points of the waves, and you look at the center wave. Show only one pulse, so now we're only looking at one particular pulse here. And you see the outgoing in red and the returning waveform in blue. And here you see a very nice one where you see there had a double return somewhere. That's in the vegetation. One more thing. You can visualize the different ways that the pulses get described. And because in a Regal, for example, you can have a high channel return. These get differently described in the pulse wave format. You can see there must be some kind of roof or something that has a really funny, really glossy return. So you see the low channel maxing out all the way to the top, and then the high channel kicks in and does a sampling of that pulse here. Okay, but that's really not what this talk was about, so I wanted to make it real quick. Software is available now at pulsewaves.org. I'm at DLL. There are some pulse tools for the basic operations that you can play around with. And that concludes my talk. Thanks a lot.
Thank you, Martin. You always leave that little carrot hanging at the end of your talk. So, are there any questions for Martin? Stephen? Could you bring the microphone around, please? Is it Martin, did it stand? Down to the front, please. Thank you very much. Yeah. Thank you.
I think your approach is brilliant, first up. The second question that actually the question I have behind that is there a way using the LASindex tool to select something that, for example, a meandering river or a single road, where it would not be simplistic for an individual to go through and click the individual portions of the quadrangle? Does that make sense? If I have a block of data, and I have a river which meanders through, and I want to pick all the points along that, is there a way I can select just the river and auto-select those points?
So the auto-select of where the river is, no. A complex shape that follows the river, I haven't implemented it yet. Right now I implement 3 not so complex shapes, namely a square, a circle, and an arbitrarily shaped rectangle. So what you could do, the simplest approach would be maybe to break it up into multiple calls and then have some more function that I would need to implement that aggregates multiple rectangles before it starts reading, so you don't read the same intervals twice. But the selection, of course, that would be part of classification. So first question, no. The second interpretation of your question, yes.
Martin, if you already talked about the super LASindex file, which includes several class files, which would just be easily to add as it is.
Yes, I thought about it. Right now, it basically exists, except it gets built on the fly each time. So when you run LAS to LAS with a query to select a subset on an entire folder of files, it will every time just quickly read all the headers, figure out which one it needs to load, and then look in each individual one. It's actually running every time you use Open Topography. They use LASindex and LAS to LAS in exactly the way I just described it, without a I was thinking of having a LUX with a double X to pre-compute this, but then you would have to sort of add and update it every time, because if you added new LUX files or LAS files to the folder, you would need to be careful that you all index them. If you just always read the folder, you're safe, and but that would be certainly possible.
Martin, thank you so much. Thank you very much.
Thank you.
Tell us more about Postgre.